Good morning, students, and welcome back. Okay, today we'll start with another topic on balancing. So we'll start looking at radial engines and balancing of radial engines. So let me share my screen. Okay, so let's get started with radial engines. So before going to the balancing of radial engines, what we'll do is like we'll look at what do you mean by radial engines. So this diagram, okay, whatever you are seeing on your screen, okay, is showing three-cylinder radial engine. Now, what does a radial engine means? Radial engine means, okay, this is a crankshaft. This is a crankshaft. Now, this is a crank. This particular thing is a crank. This is a crank. Now, on this crank, what we are doing is like we are attaching connecting rods. So, this is connecting rod 1, this is connecting rod 2, this is connecting rod 3. So, this common crank is rotating, and this common crank is attached to different engines via different connecting rods. So, if you try to assume this one, this particular thing, O, A, and 1. So, this becomes one engine. O, A, and 2, this becomes second engine. It's O, A, and 3. So, this becomes third engine. So, basically, there are three engines which are associated with this particular engine. Unlike inline engines used to have a piston, then a connecting rod, then a crank, and there was a common crankshaft. So this was crank for one, this was crank for connecting rod for one, and piston for the first engine. So it had second crank, second connecting rod, and second piston. So this was really for the inline engines. Now in radial engines, okay, this entire thing is eliminated, and what we do is like we only have this one single crank. So basically, this is about radial engines. In radial engines, the line of stroke is one of the important aspects that we need to see. So basically, if you see engine number 1, this particular, the reciprocating of piston is the line of stroke. In this one, the reciprocating of piston is the line of stroke. So line of stroke for engine number 1 is this one, line of stroke for engine 1. This is line of stroke for engine 2. This is line of stroke for engine 3. So this is one of the important aspects. In radial engines, generally what we do is like we try to keep the engine okay at an equidistant angle from the another one. If you look at this particular inline engine and this radial engine, okay, the major difference is that this engine is going to rotate in this particular plane, say plane number A. This engine is going to okay perform its line of stroke, its rotation of the crank will be happening in plane number B. Similarly, C, D, and E. So there are different planes in which this radial engine, this inline engine is operating. So basically, what happens is like we have certain force which is coming in this direction. We have certain force coming in this direction. We have certain force coming in this direction, and the bearings are attached somewhere over here. So automatically, when balancing, okay, what will happen is like there will be this component. What is this component? We call it as distance from the reference plane. We call distance between the engines. We call different distance from the bearings. So basically, since these are rotating, the forces are placed in different planes. There would be couple. There would be couple, which would be coming in inline engines. Now, if you look at this particular engine, okay, this is going to this crank is going to rotate in a single plane. So if you see like this engine would be over here, the second would be over here, the third would be on the back side of this one, on the back side of this one, and this is the crank. So this crank is attached to this connecting rod, and this crank is attached to this two engines over here. So everything is going to rotate in a single plane. What does that mean? If it is going to act, or if it is going to rotate in the single plane, so the forces, okay, what are unbalanced forces, the inertia forces would be acting in that same plane. So if it is acting in that same plane and along the plane, the forces are along the plane, then what happens is like there won't be any couple. There won't be any couple. So no couple. Okay, either primary or secondary. Secondary. So the important aspect is when we talk about radial engines, that time we need to consider, or we need to mention that there will be no primary and secondary couples. So what will be present out over there will be only FP primary and F secondary. So these are the different things between inline engines and radial engines. I would like to ask you one question, maybe like you can put the answers in the chat box. The question is, okay, you see like this type of engine, the inline engines in all the commercial vehicles. If you open like any of the truck, any of the like small vehicles, like for, say for Maruti Alto, Maruti Suzuki, or any of the vehicle out of them, you will see like the engines are placed in inline conditions. And if you go like with the racing cars, okay, we'll see like the engines are radial engines. So can you just mention why we are using this radial engines over there? And in the commercial vehicles, why are we using inline engines? Okay, what may be the drawbacks? What may be the advantages between this radial and inline engines? So that is like as an assignment for you people. So you can just have find it out and answer the question in the chat box, or you can answer and text me on my WhatsApp. Coming to the next topic, okay, this is about radial engines. Now, when we talk about radial engines, okay, we need to understand, okay, how to solve the problems of the radial engines. So basically, for radial engines, they have given a concept. So this, just try to understand that this is just a concept. This is just a concept. So, what is the concept? The concept is, they call it as direct and reverse crank. Direct and reverse cranks. This is just a concept. This is a hypothetical concept which is going to resemble, okay, this particular combination to be put and which would resemble the actual conditions of the engine. So how to go about it? That's the question. So let's start. So assume that this is a slider crank mechanism. This is the piston, the line of stroke of that piston. This is the crank R, this is L. And we know that the force, we know that the inertia force, what we derived during the inline engine, that F is equal to mr omega square into cos of theta. So this is the slider crank mechanism with piston force coming out, or the inertia force coming out to be mr omega square into cos of theta. Now to solve the radial engine problems for the balancing aspect, what we do is like, we say that this is a engine, a half engine, and the mass M is what? Reciprocating mass. Reciprocating mass. So keep that reciprocating mass, half of the reciprocating mass on piston of one engine. So this engine, say this engine was rotating in this direction, the mass m by 2 is kept out over here. So what will happen is like when we try to look rotating about this omega, so we will come to know that the centrifugal force or the unbalanced force would be m by 2 r into omega square. So this would be going along this line of action. So there would be two components. Okay, so it is at angle theta, so this would be theta. So what would be the two components? It would be m by 2 into r into omega square cos of theta, and this would be m by 2 r omega square into sine of theta. So what I did is like I just resolved this unbalanced force or the centrifugal force that is acting on the end of the crank in two components. Now, if you see like this is m by mr omega square cos of theta, this is the actual engine's component. And for our concept, like what we say, like half of that force is balanced out, or half of the force is resembling this particular, like on the putting the mass on the crank of this particular engine. Now, to have the other half, what we do is like we have a concept called as reverse crank. Now, for the reverse crank, what we do is we on the along the line of action of stroke. Okay, this is the line of stroke. So, line of stroke. So, along the line of stroke, what we do is like we consider it to be a mirror plane, and what we do is like we create a mirror image of this engine over here. So what will happen is like with the mirror image, like it will come out over here. So this one, this one. So this will be R. The direction of rotation would be in this direction. So omega over here. Mass, the remaining half of the mass will be kept out on this particular crank pin. On this particular crank pin. Now what will happen is like this is rotating out over here. So automatically what will happen is the centrifugal force or the unbalanced force will be in this direction. So what would be its magnitude? It would be m by 2 r into omega square into cos of theta. Since this is theta, this will become theta. So along the line of action, this will become theta. So corresponding angles over here. Now with this one, there will be two components out over here. So what would be the components? It would be m by 2, sorry, this won't be cos theta. This will be only along the crank, it would be mr omega square. So along the line of stroke, it would be m by 2 r omega square into cos of theta, this component, horizontal component, and this would be m by 2 r omega square into sine of theta. So if you see this one, these two things, okay, so along the horizontal line, this mr omega square cos theta, this one and this one. So it is in the same direction. So addition of these two would give me, so addition of these two, this one and this two will give me m, this will give me, so along horizontal. So horizontal would be m by 2 r omega square cos theta plus m by 2 r omega square cos of theta. So it would be m r omega square cos of theta, which would be resembling this particular value. So automatically what will happen, like it's showing that this particular position is representing the real engine. Now let's try to look at vertical forces. Vertical forces. So in the vertical forces, this is going downside. So m by 2 r omega square sine of theta going downside, and this m r omega square sine of theta. So one would be plus m r omega square sine theta. This one is plus, minus because it's going downside. So m by 2 r omega square into sine of theta. So plus minus will become 0. So vertical component would be 0. So with this concept, what we see is like if we put a mass, if we try to have an engine, simple engine, put a mass m by 2 on the crank pin, okay, it would be showing like m by 2 r omega square cos theta along the line of stroke. And if we try to put a mirror image of this particular engine, taking the line of stroke or the mirror plane as the plane, then the next engine or the mirror image engine would be giving me another force that would be m by 2 r omega square cos theta. So these two forces would balance out or will resemble this mr omega square cos theta. So this is a concept, this is a concept, this is a concept for solving problems on radial engines. Now, when we look at this one, okay, we see like there are two engines. So we need to name like what are these engines. So the main engine, okay, the main engine means the configuration of the engine, what we are going to see from the diagram at a particular instant, that we call it as direct crank. So from this basis, sorry. So on this basis, okay, this is the main engine what we had taken. So this we call it as direct crank. This we call it as direct crank. And the mirror image of this one is called as reverse crank. So basically direct crank and reverse crank. Now this particular thing we have taken it for primary arrangement. This we have taken for what? For primary arrangement. So this would be primary direct crank. This would be primary reverse crank. So using the same concept, okay, now we need to look for secondary. So in secondary, as you everybody knows, in secondary we have the secondary force as M R ohm square into cos of psi. And R, this R, what is the value of R? So R is R by 4N. So this is ohm is 2 times of omega. Psi is 2 times of theta. So these are the conditions that we have already seen. So this we need to put out over here. So on the primary crank, okay, if it was theta, in the secondary it would become 2 times of theta. The radius of the crank would be R by 4N, that we had shown it over here. This theta we have shown it over here. And it is rotating with twice that of omega. So 2 times of omega. So this is related to the secondary one. Now again the same concept. Okay, we are going to put half of the mass on the crank pin. So automatically what will happen is like it will be generating a radial component or the centrifugal force. So it would be m by 2 r means r by 4n into omega. So it would be 2 times of omega square. So again the components out over here. So it would be at 2 theta. So m r omega square by 2n into cos of 2 theta. And in the vertical side, it would be mr omega square upon 2n into sine of 2 theta. Like same thing what we have done for primary. Similarly, taking this line of stroke as a mirror plane, line of stroke is equal to this mirror plane, drawing the same diagram, and you will see like, so secondary forces would be like this two. So mr omega square by 2n, mr omega square by 2n cos theta. So it would be mr omega square upon n into cos of 2 theta. And the vertical component, this component and this component would be cancelled out. So automatically it would represent the actual engine, that would be mr omega square upon n into cos of 2 theta, which is nothing but the secondary force, that is mr omega square upon n into cos of 2 theta. This is we have already seen when we looked at balancing of reciprocating engine for single cylinder. So this is a concept that we are going to use for solving the numericals. So students, I will stop over here. And if you have any questions related to anything related to radial engines and concept between direct and reverse crank, please comment me in the chat section. You can email me, you can like send me a WhatsApp message. And in the next lecture, what we'll do is like we'll see about the numericals to be solved for this particular topic. So let me stop presenting it out. Let me stop the recording. Okay, so thank you guys. Let's meet you in another lecture. So thanks for your time. Bye.